and I am a student at the Applied Artificial Intelligence Lab in the Oxford Robotics Institute, where I'm very proudly sporting my stash. Yeah, today I'm going to be talking about a relatively new field, a field that I'm very excited to be working in, which we have aptly called here robot dreaming. Um, of course, this does actually have many names, and as you'll see, many people will call what we're going to see here today world models or applied AI for robotics or learning and imagination. But my goal is to give you an oversight as to what this field is, what the current status quo is, what some companies have done, and to give a brief introduction into robotics and a brief introduction into generative AI, just so we can see, try and understand what is actually going on. As Prahavi has already very kindly said, I do have the chat open here on my phone next to me. I will be asking questions throughout the presentation, so please answer them so that I can see and like I can react to what you guys are saying. And likewise, if you have any questions at any point, pop it in the chat, and if there's time, if it fits in, I'll answer them there. Likewise, if I say something that doesn't quite make sense, or if you would like me to go over something again, pop that in the chat as well. Speaking of, let's start off with a simple question. Namely, what do you think of when you think of a robot? So this is your chance to get that chat flowing and just tell me your ideas. Well, so lots of people will think of more classical types of robotics. So the most common will be like the Boston Dynamics Spot, or robot arms as you would see in factories. Some people will even think of Star Wars, think of C-3PO or the little droids that roll around there. Most people assume that robots, when used in industry, are mainly used in factory settings, which is true. But there's also a massive market for robotics when it comes to more um, mundane household things, for example, gardening. This robot you can see here is called Hull. It's something that the Robotics Institute developed to garden at Blenheim Palace. Likewise, there's a lot of work working with other researchers, doing more environmental surveying and off-roading, and there's lots of robotic ships floating around. But the key point here is that there are many different types of robots, and these are the more classical types of things you can see, but actually the definition of a robot is way broader than that. And in essence, a robot is pretty much anything that can interact with the world. So a wind turbine, in reality, you've got a generator, you've got some kind of control system, you've got sensors, you've got all the components that make a robot, and everything under the hood is completely the same in a wind turbine as you would have in these systems, except of course the control logic. But fundamentally, it's all the same. Next, I want to ask you this other question. What do you think of when you think of AI? This is obviously a topic that has gained a lot of fame and popularity recently. If you have any specific things you think of, please pop that in the chat as well. Um, but the big thing, as I would expect, are chatbots. So you've got your ChatGPT, got Gemini, you've got even Siri. It's a type of AI, and all of these are associated with these big clunky server rooms. Um, that process, gigaflops of information, gigaterabytes of information every second. And whilst this is true, and there are a lot of people working on this, there are a lot more people working on the modeling domain and on the embodied AI domain. And what's different here, what I mean by embodied AI, is AI that you upload onto a small device, whether that's your phone or a robot or a weather station, something embodied in some form of hardware. And the challenge that this presents is that you cannot have infinite amounts of energy, you cannot have infinite amounts of data, and you cannot have infinite amounts of computation to go on there. So it's a very different field, and this is where most of the work is at. And that is the field where AI can have the biggest impact on robotics. So naturally, we've got Naturally, we've got robotics for healthcare, manufacturing, agriculture, blah, blah, blah. Those are the common potential impact areas that we know. But the problem with robotics in the current day is that, well, robots aren't smart. In fact, they are really, really dumb. They do exactly what you tell them to, which ends up being a problem because you usually tell them to do the wrong thing. And to explain a bit more what I mean when I say robots aren't smart, I'm going to show you a good example. A robot can account for some eventualities. It can try and interpret the world. It can try and understand what's going on. But at the end of the day, it only knows what you've shown it. So if you've got a construction robot that, does like a pick and place task, picks up bricks, moves them around, and it does this good and well, in 9 out of 10 cases, if you then remove the bricks, the robot will just do nothing, or it'll continue pretending to pick up the bricks. Now, that might seem like a trivial example, and of course, that is a case that you could program into a robot, say, if the bricks are missing, don't do something silly. But the key point is you cannot program for all eventualities. I've got another fun example for you. The graph that you can see on the page is from a model performance graph from a robot that has been trained to fold t-shirts. They trained this model to fold t-shirts in March. They trained this robot, and in March, it had 100% accuracy of being able to fold t-shirts. And this company noticed, so this company is called 1X, they noticed actually that as time went on, with nothing changing, it's the same algorithms, the same robot, the same t-shirts, as time went on, the robot became worse. And in fact, they could measure from here, they measured from March to May, it became a lot worse, from being 100% reliable to only about 60% reliable. The reason that the robot gets worse is actually the weather. Because if you imagine what the sun is like during the day in March and what the sun is like during the day in May, the actual brightness of the surroundings, the way the world looks like, changes slightly, and the color of the world changes slightly. And this was enough to throw off this robot and to stop it from being able to quite literally um, fold a t-shirt. I'm going to go into more depth now in what I do. So at the Robotics Institute, we've got a very wide range of robots. These are all the ones that we have. And I live in the intersection of these robots and AI, trying to make them smart. I mostly work with this bimanual manipulator called Frank, which is short for Frankenstein's monster, which you can see here with the postdoc in my lab. I'm just going to give it a little wave. Frank is mostly built to do assembly, so, putting together pins and beams and that kind of stuff. And if anyone wants to know more why that is what we're working on, feel free to ask me afterwards or during, and I can go into more detail on that. So let's start with the basics. What do we even mean by a robot? Well, as I said before, it's anything that can interact with the world. And that involves a very intricate pipeline where you start with vision and sensing. So that is, touch sensing, distance sensing, cameras, all that stuff. And in the top right here, you can see what sensing looks like when you've got a laser scanner. That's kind of what your standard Tesla or Waymo autonomous car would see. It's this point cloud 3D sense of the world. But the problem with that information is it's a bit useless by itself. And so we've got this other layer called perception, where you process that information, you try to get some semantic meaning out of it. That's kind of what you can see in the bottom right, where you've drawn bounding boxes around humans. You've taken that information, you've taken camera information and tried to do something useful with it. That then goes on to high level planning. So that is deciding what you're actually doing, moving, saying something. But that's all good and well. If I decide I want to walk somewhere, that doesn't make my legs move. So you've also got the low level planning, which decides, given what I want to do something, given I want to move somewhere, what are my legs actually going to do? And then that goes off to some pipeline that tells that to the motors, and it controls the motors to make sure they're actually doing what they're supposed to be doing, and it's this whole thing. But the important thing is that there's labs who work on every single step of this pipeline. So there's people who only do actuation, people who only do control, people who only do low-level planning, vision and sensing, perception, blah, blah, blah. I live in the high-level planning domain. Combination between high-level and low-level planning domain, but it's the bigger picture of let's give this robot a brain. And traditional robotics you've focus on things like path planning or model predictive control. So that's a bit more on the low level side, but there are these algorithms that are designed to do one exact thing, um, and they're very good at that. But as I said before, they're not smart. If anything changes, they won't be able to adapt to the world, and they won't be able to, fulfill their task. So let's go a little bit of a tangent, and let's speak about how AI comes into this. Well, AI has had this huge explosion over the past few years, where you've got lots of household names now, like ChatGPT, Google Bard, um, and all of these that have, in many ways, revolutionized not just how advanced industries work, how programmers work, but also how children are taught in schools and so on and so forth. But the strange thing is, all of people only really started to take notice around 2020 or 2021. Um, but this graph goes a bit further back. In fact, it goes a lot further back. And the whole concept of AI that we're building on and we're working on today is actually started in the 60s. So the first neural network was defined in the 60s. So the question is then, why now? Well, um, it's quite simple, actually. It's because we've got a lot more data, we know how to process it better, and we can process it faster. So the graph I'm showing here is Moore's law. It's how it's effectively how good our computing is over time, and you can see it is massively grown. This and having the growth of the internet giving us multiple scales more data than we've ever had access to, and smarter algorithms for processing this data has let us scale all of the algorithms that define what we call AI. And I want you to just take note of the y-axis here. So this is a logarithmic scale, and you can see actually the jumps between how big these models are measured in how many individual parameters you're learning are extreme. I mean, in the 1960s, 1,000 parameters couldn't really do very much. And now we're talking about 1 trillion parameters, um, which is an obscene number to think about. 1 trillion parameters. Imagine how many, like, the vast scale it takes, the vast number of computations it takes just to go through a model once to get any kind of output. So all these things I've just spoken about, ChatGPT, etc., they're all a type of AI called generative AI. Generative AI is the name is kind of self-explanatory in the sense of it's AI that can generate things. Um, but what it specifically means is generative AI is any AI that models a probability distribution. And I think you need to take a step back and think about what it actually means to have a probability distribution, because it's quite easy to say you've got a probability distribution over the heights of humans around the world. Um, but it's not that easy to think about probability distributions on a massive scale. And the probability distributions that these massive models scale are on the scale of modeling the probability distribution of all text. And that's a weird thing to think about. Having one probability distribution that describes all of writing, every single possible way of combining characters. At the end of the day, what ChatGPT models is literally that joint distribution. What is the probability of all the text? And then if I want to generate something, I ask the probability distribution, what is the probability of the next word appearing? And it'll give you a list of like all the possible words and their probability distributions, given that the first few words I've given it are X, Y, and Z. So if you give it the sentence, I don't know, the car has blank wheels, and you ask it to fill in what blank is, it has learned the probability distribution that associates when you're talking about cars and wheels in a sentence that you should have the number 4 there in the middle. And that is probably a bad example because that actually describes better what a transformer does. So a transformer is the architecture that all these big models are built on, and they are built on the concept of attention. And what attention is this idea that actually you don't care about everything you see. If you want to predict the future, if you want to predict a certain word, you only care about some things, right? So in this case, if I have the sentence, I was walking down the road and I saw a red car with blank wheels, the fact that I was walking down the road doesn't really matter. Even I would go even further and say all of the words like the don't matter, all the words like don't matter. And the concept of attention is saying, actually, I'm going to only focus on the word cars or car and road or whatever. And I'm going to only take that, and that's going to give me all I need to know to be able to predict the word for here. So, but generative AI in the terms of text is one thing. Generative AI can also be extended to talk about images. So this gets even more abstract, right? Because now you're talking about what is the probability of a certain pixel having a certain value between 0 and 255, given that the previous 10,000 pixels have these values. And it is that simple. I mean, it is that big and crazy, right? It is genuinely, I have these numbers and I'm going to predict the next number. And that, if you get an advanced enough probability distribution, that gives us the ability to make coherent and even photorealistic pictures. And of course, that depends heavily on having more than enough data to do so. Cool. So let's tie this back to robotics. Well, as I said before, robots are pretty good at doing the kind of bog standard thing. They're good at knowing where am I, whether that be through GPS or by building a map of the world. They're good at, if you tell it to move an arm in a certain way, they're pretty good at doing that. What they're not good at is common sense reasoning. It's this whole deeper understanding of the world that lets us know that a picture of a t-shirt is the same than another picture of a t-shirt, even if the lighting is changed slightly. That seems like a simple concept, but it's really, really difficult to implement in practice. It's obscenely difficult to implement in practice. That kind of multi-step reasoning, that kind of more advanced process behind decision making is what we need AI for. Let me give you another example of multi-step planning and where something like AI could be useful for a robot. I know I sat down today knowing that I would give this talk, and I knew that I would use my laptop. And so if I asked a robot to prepare this presentation for me, it would have probably placed the laptop on the table, made sure that a chair was there, and that was it. For as far as it knows, it has now done the planning and the preparation for me to sit down and do this presentation. However, the multi-step reasoning that I've had to do when I sat down is I had to say, well, I'm going to be using my laptop. My laptop's going to be using up charge. Hence, I should probably take my charger out of my bag and plug it into my laptop. That seems like a very simple thing to do. But if you ask a robot to open up a presentation on a laptop, this extra step of saying, I am probably going to need power isn't trivial. Likewise, if you say, I'm going to fly to another country, at some point in the weeks leading up to your travel, your brain is going to go, they've got different power plugs there. I should probably buy a travel adapter. And now, whilst it would be cool to have robots traveling, I don't think they'll be doing that anytime soon. That kind of thinking, that kind of precognition and what you're going to do is something that is needed for all these tasks. So I think now that we've had a start of a look at generative AI, we can tie this back to the concept of robot dreaming. What robot dreaming actually is kind of up for debate, but I'm going to convince you of this process called a world model. A world model is, as the name implies, a model of the world, but more specifically, it is a hyper efficient, incredibly quick way of processing what the world is doing. And most importantly, it is a way of throwing out all the things you don't care about and only keeping the things that you do. So let's define this concept a bit better. Let's say for our purposes, a world model is effectively just an understanding of the world. And typically what we mean by that is a dynamic understanding of the world. So for example, if you have a ball, I know that if I am going to push the ball is going to move, right? So that is a dynamic understanding because it's going through time and it's building up an image of, different forces and how they interact with each other. And this idea of efficiency and throwing away things is saying, maybe it doesn't matter what color the floor is as long as it's flat. So all I really care about is are these dynamics and is this pushing? So a world model traditionally, of course, there are way more advanced architectures at the moment so far, but in its simplest instantiation, a world model can be broken down into two constituent components. The first component is a compression of the world, which is seen here in the VAE, that stands for Variational Autoencoder. And the second component is a probability distribution. This is your generative part, a probability distribution that describes the evolution of the world. In this image, it is depicted MDN-RNN, which stands for Mixture Density Network Recurrent Neural Network. And the key thing here is that when I say a compression of the world, what I really mean is taking um, taking what I see and coming up with some representation, some set of numbers that keeps everything I need to know and throws away the rest, right? And this probability distribution, in essence, if you've got a probability distribution that describes the dynamics of the world, what you've really done is you've understood how the world actually works. Let's go into more detail to see what a VAE looks like and what it does. A VAE takes a high level representation of the world, a high dimensional representation of the world. So that's typically an image. And it says, actually, as long as I know that I am working in this certain bounded world, I don't need to know I don't need to know everything to describe what is going on, right? I can describe the entire world with only a certain set of numbers. Now, let me give you an example to describe that better. Let's say the world you care about. And I do mean, like, imagine like that this VAE will only ever see one thing, which is a black image with a square inside of it. And the square is always white, the background is always black, and the only thing that changes between images is where this square is in the world, right? That is it. This is your world. And that might seem like a trivial example, but in many cases, you can break it down to this. If you've got, for example, a robot trying to pick something up, in essence, all you care about is where is this one thing, and the rest doesn't matter, right? So you care about where's this one thing, the rest doesn't matter. So for all intents and purposes, everything else is black, and the one thing you care about is that white square. Now, this image will consist of lots and lots of numbers. So if an image is RGB, that means you've got one number for every red, green, and blue element of a pixel. And then if you've got an image that is 600 by 600 pixels, you now have got 600 by 600 by 3 numbers describing this image. That's a lot of numbers to work with. And if you ask something to predict the next 600 times 600 times 3 numbers, given the current 600 times 600 times 3 numbers, that's a lot of computation that you're going to have to go through. And in most cases, that as a process doesn't work. So what a VAE does is say, all right, you've got this world. I know that the background is always black. Hence, I do not care about the background. This is not something I don't need to know. You don't need to tell me the color of the background for me to know what this image looks like. So you compress all that information. At the end of the day, you can compress all that information into, in this case, 2 numbers, right? The x position of the square and the y position of the square. If the square can be different sizes, you can do it in 3 numbers, x, y, and size. And a VAE says, give me an image, I'm going to compress it to those 2 or 3 or 4 numbers, and then I'm going to uncompress it again into the original image. And if I can do that, then I know that those numbers I have in the middle are all I need to know to describe that world. So does anybody have any questions about that? Because that is quite a fundamental concept to understand what's going on here. You take an image, you compress it into some representation, which gives you all the information you need to know about the world, and then you uncompress it to give you back your original image. Well, let's take this to a bit of more of an advanced, a bit more of an advanced setting. Let's look at the video game Doom. Right, so here we've got it's a game I don't actually know what year it's from, but it's a video game. The question I'm going to ask you, and please put your answers in the meeting chat, is how many numbers do you think we can compress this world down to? How many numbers do you think it would take to completely describe what is happening in this game? I'll give everyone a second just to write down the numbers, remembering that yes, okay, actually, good question. In this case, ignore the heads-up display. You could, of course, argue that the heads-up display is pretty much constant, except for a few numbers changing, but ignore that for now. Just think of all the possibilities that could be there. 100? 100 is not bad, actually. Well, if you've got billions of numbers, you could describe, if you've got billions of numbers, you could describe any image realistically, right? Because an image only has millions of numbers. Ivan's actually gotten it. 15 is the right answer, and I'm going to show you a little demo here. So that video was taken from this paper, which describes world models and dreaming. And we can actually go down here, and they've got the little variational autoencoder. You can see they ignore the heads-up display. And what I can actually show you is this process. So the VAE decodes everything down to 15 numbers, right? So this is the input, this is the image that you get back, and everything we really need to know are in these 50 numbers. And I can actually change them here. You can take a note of the website if you want to play around with this yourself. It's quite cool. And you can see that by just changing these numbers, I can actually control things like where the enemies are, where the bullets are, how many bullets there are, so on and so forth. Including, moving left and right, which we should be able to do. Yeah, so moving away from the wall like this, and this way, so also moving left and right. It's quite cool, that, isn't it? And this is the question of what you need to know. As you can see, the input is already quite blurry. The reason for that is the smaller you make an image, the more kind of information you throw away, the more blurry you make it, the easier it is to work with, and the quicker you can get something useful out of that. But then the output is even more blurry. And that is because even though it looks a bit bad, you can see everything you need to know in order to play the game. Right? You can see the bullets flying towards you, you can see where the enemies are, how many there are. You don't see all the details from the walls, for example, but you see enough to know that a wall is there. To answer the question of how does the VAE decide what is needed and what is not needed, um, that's a good question. It's not via attention. It's the loss function that you give it is effectively reconstruct this image as good as you can. And what it does is it says, I've only got 15 numbers to work with. So I'm going to take those 50 numbers and I'm going to fill them with the most useful thing I can. Right. So if you then, so if it can get away with learning, if I move left to right, if you can get away with learning, if I move left to right in this world, and learning literally what the image looks like at every time step, it will do that because that is easier than learning an actual 3D representation of the world that you can move around in a 3D space. It's much easier to do that than learn a 3D model. Likewise, being able to reconstruct those little lines on the bricks isn't really worth the capacity of the 15 variables. So the what does it keep, what does it throw away process is effectively like it does the greediest choice it can. What can I put in those 15 numbers, which will give me the best improvement in what I can see when I reconstruct that image? So that's the variational autoencoder. That's quite cool. Next step is the world model itself. You skip ahead this. And the world model itself is just some neural network which implements this probability distribution. And this probability distribution says it's got four components, well, three variables, four components. A is what action I'm taking. So am I moving left? Am I moving right? Am I moving forwards? Am I moving backwards? Z is the current compressed image of the world, which is called a latent variable. Latent meaning it's like some latent means you've got something that is hidden that explains the rest, right? It's something that you cannot measure directly, but in this case is enough to describe the world. And H is something called a hidden variable, and this is effectively memory, right? For all intents and purposes, if I've got a world, if I'm struggling with something like object persistence, if I ignore that H, if I look at an object, I turn around and I turn around again, without memory, I will not know that that object is there. But by keeping that memory component, you can fix that issue. So this is a really simple equation. Obviously, implementing it can take many forms, whether that's so this is the generative component, so this is effectively what a transformer does. This is what any generative system does. But if you do this, if you manage to get a good enough model of this, what you can do is you can simulate the world entirely in this world model, and that simulation is called a dream, right? So you can say, all right, I've taken an image of the world, I'm gonna put it in, I'm gonna step left, I'm gonna see what the image looks like, I'm gonna put that in again, I'm gonna go again and again and again. And in the context of video games, what that lets you do is it actually lets you play the video game, but in a latent space. So imagine you've got this, car racing scenario, right? You're just trying to drive the car around. You learn some kind of variation autoencoder which manages to reconstruct this world. And again, it chooses to ignore some features and keep other ones. Like it doesn't do the blocks and it doesn't what should we call it? It doesn't keep the blocks and it doesn't really keep the detail on the car as much and blah blah blah. Also, side note, if you're wondering why the image goes like this sometimes, it's because I'm putting in completely random inputs. And so there is nothing preventing the variation autoencoder from saying, actually, if you give me garbage, I will spit out garbage, right? I'm saying if I give you something random, it'll give me something random. But you take that, and then you generate the videos, you train your world model, and then you've got a dream. So what you're looking at here is the world being forward propagated by this world model. And at every point, you take your action, you predict the future, and you play that out. This is actually, if you go to this website, you can actually drive the car itself. So I'm doing the red bar on the bottom right shows that I'm doing it. It is really difficult to drive. It's not good enough. Um, it's not easy at all, but you can do it. You might be asking yourself at this point, what is this? This looks like crap. It's obviously not easy to drive. Why would that be useful? Well, the answer is computational efficiency. If you have to work with, let's say, not even a 600 by 600 image, but you have to work with a 256 by 256 image, that means that the image describing the world has 196,000 dimensions, 196,000 numbers that you have to make a decision about every single time you want to predict into the future, right? So that's what a traditional simulation does. But now we're only working with 16 numbers. And you might ask yourself, well, how much faster could that be? Computers are pretty fast. Well, if we do some math, any kind of computation in this field will be performing matrix calculations. And at the moment, our best algorithms can kind of scale the amount of time it takes per computation, depending on around between n squared and n cubed, where n is the number of numbers that are in the matrix, right? So that means if I'm now processing something with 16 dimensions as opposed to 196,000, I'm actually processing data 150 million times faster. For context, when I'm working in the lab and I'm trying to train a world model, I can often go and I can often process 40 million frames at the same time. That means for every second, for every second that I could be looking at a screen, I can actually simulate 40 million seconds. And you can imagine what that means in terms of neural network training, in terms of robotics training, that I now have a simulation that I can go through really, really, really quickly and get some understanding of the world out of it. Um, what what is this useful for? Well, let me paint you a picture. Let me give you the absolute best case scenario. Right? So this is something that is years away from happening, but we know kind of how we would do it. Um, we're just working towards solving that problem. Okay? Imagine you have a robot dog with an arm strapped on top of it. And this robot dog has a world model. It knows what the world looks like, it knows what all the component elements of the world are, and it's got a list of things that it has learned to do. So you've got some kind of decision-making process, which in this case is adjustable, learnable, and you've deployed it in the real world. It's learned how to walk around, it's learned how to, I don't know, maybe open a door. But now you tell it to pick up a cup from a table. It's seen a cup, it knows what a table is, it knows what a cup is, but never in its life before has it ever picked up a cup, right? So the traditional method of robotics, if you say you're using reinforcement learning, you're using some kind of learned agent, which doesn't use a world model, is to go try it out. Is to go get the robot to try pick up a cup, and obviously it has no idea what it's doing. It's going to fail. Best case scenario, it's funny. Worst case scenario, middle case scenario, you've broken a mug. Worst case scenario, you've broken a 250,000 pound robot. All right, that's not useful. Is once it's tried it, even if it's not broken, it might have to try it 100,000 times in order to learn how to pick up a cup, and that's just not realistic. Right? There are some industries where you can let something play with the world, let a robot play with the world to figure out what's going on and to figure out how to solve tasks. But there are also many more industries where that's just not the case. So you tell your robot, I want you to pick up that mug. And the first thing it does is it goes into its dream, it takes the current world, it puts it into its dream, and it predicts into the future, right? It predicts and it just says, this is what I would do if I would do this in real life. And the dream is not perfect. It may be blurry, it may be missing stuff, it might be really hard to control. But the important thing is the dream in this case is good enough to know, can I pick up that mug? So it goes to the dream, it tries to pick up the mug, it goes, well, crap, I can't do it. And it reports back saying, actually, if you asked me to do this, I would break myself, I would break the cup, I can't do this. This is kind of like introspective thought that normally only humans can have, right? And then we take that one step better. We take that one step further. We say, not only can you, now that you have this dream, not only do you know you cannot pick up a mug, but the robot's going to simulate 10,000, 100,000, a million tries of picking up a mug until it can come back to you and say, actually, just because you've told me how to do this, and because I have a world model, I am now 99% certain that I can go over to that table and pick up that mug. Whether that actually will work, who knows, right? 99% certain in a dream doesn't necessarily mean 99% certain in real life. But the hypothesis is that that is good enough. And that is good enough that without doing anything extra, you can teach, the robot can teach itself how to do new things. And this goes on to, the value of a world model in robotics, the value of having a world model over a more traditional robotic system, or even a more traditional learned system. Well, the first one, as I said, is efficiency. If you have a world model, training in it is really, really fast. The second thing is transfer, right? It might take you 3 months to teach a robot how to reliably pick up something and move it somewhere else, or how to, do an insertion task, put a pin in a hole. Then, if you wanted to open a microwave, it might take you another 3 months. But what if you just spent 4 months in the first place, or 5 months, learning a world model, and now whatever you wanted to do, you can transfer. You've got this, the robot has this intrinsic understanding of how the world operates, and you can transfer that and take that around with you and do everything from there. The next thing is obviously safety. There are many, many scenarios where you cannot test things in real life. And so you want to test things out in simulation. Simulators are pretty good these days, but simulators can't do everything. For example, you can easily simulate physics, but is what you can't simulate is how the world around you is going to evolve in terms of people and other cars on the road, things like that. Actually, I'm going to skip ahead a little bit, and I'm going to show you this video. So this video is from a company called Wave, and what you're watching right now are videos generated by a world model. So nothing here is real. The world model, the input you give it is action. So they're driving forward, driving left, driving right. Not only is it photorealistic, but you've got other cars, right? Like you've got all this behavior. You've got people crossing the road. You've got cars stopping when people cross the road. Those aren't things you cannot program. And you can, but you cannot do it for every possible thing that could happen, right? So now you've got this platform where if a company like Tesla says, we've got this self-driving car, and the government says, yeah, but if a child walks in front of it, what will it do? Well, now you can answer that question because you've got a world model that you can give it the actions to and it can simulate forward. Of course, these things aren't perfect, right? Like there are going to be mistakes. You can see actually towards the end here, there's actually a car, this car here just disappears. If you look close enough, you'll realize it's not real, but it's good enough. It's good enough to learn what is going on. Um, yeah. So I guess the next part of my presentation is showing you how far we've actually gotten from this. So the first example that this like ideal scenario that I've given you where a robot teaches itself new skills, and one of the first things that researchers did is said, oopsie, how do I mute this? It said, well, we're gonna give a robot the ability to learn about the world, but nothing else. And all it does is it tries to figure out how to walk. Except it's never heard of gravity, it's never heard of the floor, it's never heard of walking. It has literally no one's like images don't mean anything to it. It is more newborn than a newborn, you know, it's got no concept of the world. But now every time it does something, it is adapting its own world model, it's adapting its own understanding of the world, and it uses that to then train in the world model what are the next steps I can take? What is the most likely thing I can do? And using just that, from having no understanding around the world, in an hour, you've got a robot that can actually walk around. And yeah, I guess that's yeah, walk around. And it gets quite good, right? Like it gets after a while, it can stand back up. You can bully it, well, which I don't recommend. You never know when they're going to fight back, but it gets quite good. Um, another cool thing, skip that one. Another cool thing that a company has done is they've generated a world model of like, the world, but from a household perspective. So the video you're watching here is also entirely dreamt up in a world model, right? Everything you see here is not real, but it's like a video game. You can control what the robot does, and it's really cool, right? And it can teach itself things in the world, and it can teach itself things that are actually extremely complex. If you've ever seen if you've ever seen a simulator try to model cloth physics or fluid dynamics, not only are they horrendously slow, they're also really bad. Um, but this clearly can simulate folding a t-shirt, which is crazy. And it all runs on a robot. There are a few funny things that happen in this video, actually, which which show us kind of the limitations of this technology. And it's quite funny because the limitations that we see here are actually very similar to the things that we see both in the animal kingdom and as humans, when humans try to learn, when babies try to learn. Things like object persistence, things about well, okay, object persistence, and then this one's really funny, self-recognition. In this video, in the world model, the robot is looking at a mirror, and it clearly knows that, you know, there is something else there, but it thinks it's a different robot. It's got no idea that actually it's looking at itself, got no concept of what a mirror is. And you can see that because obviously the actions aren't mirroring in the world model. Another fun example is sometimes, you know, physics just breaks. you've got a plate just floating in the air. It's quite funny. Or, you've got awkward distortions that can happen in the world. I'm not sure if they've got the video of that here, but we might as well actually just look at it if I can. There you go. What was I going to say? Oh yeah, I was going to say object persistence, right? Um, where is it? Here. For example, you look at a spoon. No, it's not that one. Oh, where is it? There is one where it picks up a block and then the block disappears. There you go. This is it. It picks up a block and then for a split second it cannot see the block anymore, and so it disappears. It's literal childish things, object persistence, something that we feel like we should have solved. Yeah, there's just many, many videos of companies trying to do this, and there's many non-robotics related things as well. What you're watching right now is a generative model, which is a world model that you can give text to, and it'll generate a completely playable video game that tries to simulate the future of the world in this latent space, decode it back into images in a playable way. It's quite cool. And there's a lot of cool technology that's going to come out of this. Um, and yeah, and I'm excited to see where it goes. If you're interested in this stuff and you want to learn more, that one website that I was talking about earlier, the worldmodels.github.io, has these cool demonstrations of learning world models in the video game settings. If you're looking to get involved with generative AI, there's this really good textbook which is available free online called Generative Deep Learning, which has free code examples that can go alongside with, and it's what helped me get into it. And it's really great. And otherwise, if you've got any questions, feel free to contact me.